In our last video, we talked about the concept of voltage. And voltage is actually the amount of energy per unit charge. So what that kind of means, think of it this way. Voltage is energy per charge, or energy over charge. But remember that energy is the same as work, and so it's the work done per unit of charge, or compared to the charge. And remember that work is equal to force times distance. And so voltage is kind of like the force that pushes a charge through a certain distance. And so voltage is what makes the electrons actually want to move. When we start talking about electric circuits, that's exactly what we want to do. We want to push electric charge through a circuit a certain distance, and we do that by applying a force. And what that then means is that we're basically talking about electrical energy. So you see how voltage kind of relates those two together. So you'll often hear that voltage is a force. It's not quite a force, it's like a force, but it's more specifically a force pushing a charge through a certain distance. But it still gives us the idea that it's pushing, right? Voltage is what's responsible for pushing charges. And when we start talking about electricity, we're going to be talking about electrons for the most part. But voltage can push any kind of charge, negative charge or positive charge. So it's pushing charge. Now, the other thing that we mildly discussed a little bit was the flow of the actual electrons themselves. The next important thing to learn about is current. And current is basically the rate of moving electrons. Actually, you know what? I'm going to change my mind on how I word that. I'm just going to make it simpler. The word rate sometimes is confusing. So it can be thought of as the amount of charge moving past a point in a certain time. And you can think about a river. If the current is strong in a river, it means that a lot of water would be moving past you, right? If you were sitting on the side of a river and the water was moving past at a very slow rate, then the amount of water, think about taking a cross-section of the river and all this water as it's moving down the river, and you're sitting here at this point watching it. Well, if a lot of water goes past at a certain time, then you'd say it's a high current. But if you measure this to be only a little bit of water moving slowly, right? If it's moving faster, a bigger piece will go by. So I can draw that better for you. Think of it like this. If the water's moving fast, then all of this water might go by you in a second. That's a lot of water. But if the river is moving slowly, then, and here you are, then only a tiny bit of water will move past you. So this is a small current, right? And this is a large current. And so with electricity, we're not talking about water, but if we talk about, say, a wire, then inside that wire is charge. And this charge is moving. If a little bit of charge moves past you in a certain time, let's say you're here, and only that much charge goes by, we would call that a low current or a small current, right? So it means a small amount of charge is passing by you. But if we had a faster current, right, or more. Now the interesting thing about electrons is they pretty much go the same speed, but look what I'm doing. I'm going to have, it's going to be the same amount of space, but you can see how we have a large current because we have more electrons crammed into the space. So unlike water, which can go at different speeds, the speeds of electrons tend to go pretty much the same. But if there's more of them going, you get a bigger crowd. So you can see how on the bottom, even though I've drawn these two lines or two spaces to be about the same width, one has more electrons in it because the crowd is bigger. So current could be thought of as how big is the crowd, right? How many electrons are moving. So I'll go back up here. It's the amount of charge, or you could think of it as how many electrons are moving past a point in a certain time. Okay? And the other concept that we talked about was resistance. And resistance is basically it's caused by the structure, the atomic structure, whatever the matter is made of, and how well it holds its electrons or lets them move freely. It's caused by all kinds of things, but generally resistance is a property of the matter that the electricity is going through. So resistance, basically, we could say it resists the motion of electrons. So it works against the current, the motion of charge. Okay? And there are many types of resistance. Resistance generally, though, is caused by the substance that the electricity is trying to go through. So you could kind of think of resistance, if you wanted to use the river analogy, a nice river like this, where the water is flowing through the river nice and easily, has very little resistance. But if you have a river that has large rocks in it, and maybe a dead tree and it fell across the way, and it kind of looks like a face, but it's not. Another rock over here and rocks. Well, the water then is going to trickle around, it's got to work its way through, and this is going to cause resistance, right? It's going to try to get in the way of the water. And so the water is not going to be able to flow as easily. So you can think of resistance as the stuff that gets in the way of the electrons, right? Things getting in the way that try to keep the electrons from moving. All right. And of course, it stands to reason that the amount of current, right, will go up. Current will rise if you push it harder. So if the voltage goes up, then the current will go up, right? But current will also get faster, or it will go up if resistance, the stuff that's in your way, goes down. See, there's a little bit of a difference. Voltage causes current to go up. Rising voltage, rising current. That's what we call a direct correlation. Whereas with the other, resistance goes down and current goes up. They're kind of moving in opposite directions. We can put this together in a mathematical form, and in fact, a fellow by the name of Robert Ohm did it. And in the mathematical form, he discovered that voltage is equal to the product of current multiplied by resistance. Now we use symbols instead of words. The symbols are pretty straightforward. For voltage, it's V, and resistance is R, but for current, we use an I. And that's because the C is already used for other things. So current I, all right? We just have to get used to that. And this little relationship here is known as Ohm's law, after Ohm's law, after Robert Ohm, who was the fellow who put it together. And it tells us the relationship between these three things. Okay? So we can use Ohm's law to help us figure out a voltage, current, or resistance. So let's do a couple of examples of how Ohm's law might be used in a problem. Examples, all right? Number one, let's say you have a light bulb. A light bulb has a current. Now you remember from grade 9 that current is measured in amperes or amps. So a light bulb has a current of, let's go 10 amps, 10A. Okay? A stands for amps, I stands for current. A is a unit, I is a variable. You've got to get all your letters straight. 10 amps running through it. At a voltage of 110 volts. That's kind of similar to what you'd find in your house. If you had a light bulb, it may have about 10 amps of current and about a voltage of, say, 110 volts or so. All right. How much resistance? Is produced by this light bulb. How much is this light bulb trying to stop the flow of electrons through it? Well, we can use Ohm's law. And we can write that V equals I times R. Now, you probably learned a little triangle, maybe, and you wrote V and I and R, so you learned that you could cover up one and get all the others. I tend not to use this at all. I don't think it's a very good idea because it doesn't train your brain to think mathematically. It trains your brain not to think at all, right? Watch how we do this. We have this relationship, and that's all I have to remember, V equals IR. I don't have to remember I equals V over R and R equals V over I and all those other things. I look at my question and I put the numbers right where they belong. You can see it says there was 110 volts, so I'll put that right here, 110 volts. And I won't put the V for volts in anymore because notice how the V for volts looks a lot like the V for voltage for the variable. And so you get all confused with all these V's. So when I use the formula, I don't put the units in. We know what they are. Okay? So we have V equals, now the current was the 10 amps. Amps is current. And so it's 10 times R. Now we use the rules of math to finish this off. In the rules of math, we can divide both sides by 10, because you can do whatever you want to both sides. And what that means is 10 multiplied by R and then divided, it cancels is what we like to say, right? But 10 divided by 10 is like a 1, so it's like 1R and disappears. And over here, this would be 11, right? 110 divided by 10 is 11, and that would be the resistance. And then at this point, we should put in, maybe I should leave a little more room there. Now that we're done the math, we should put the unit, which is that funny looking thing called an ohm. It's a capital Omega. So this is a resistance of 11 ohms. All right? We can find something different. We can do a question that asks for maybe, well, let's try this one. A heater has a voltage of 80 volts across it. I'm using the word across it because voltage is a measure of the amount of force pushing through a distance, kind of, through the heater a certain distance. So voltage across it. What that means is that there's 80 volts causing electrons to pass through the heater. Okay? A heater has a voltage of 80 volts across it and a resistance. Now, this is going to have a high resistance because heaters work by heating up. And if you have high resistance, those electrons will push, and they'll push through this substance And they'll heat it up because they're being resisted so strongly, and we'll get a lot of heat. So high resistance often produces a lot of heat. A heater has a voltage of 80 volts across it and a resistance of 2,500 ohms. How much current will flow through it? How much current will flow through it under these conditions? Well, guess what? V equals I times R. Nice and simple. And you probably did questions like this in grade 9, so this is all review for you, right? So there's the voltage, 80 volts. I'll put that here, equals. We don't know what the current is. The question is asking about the current, so I'll just leave an I there. And then it says the resistance is 2,500 ohms. So I multiply that by 2,500 ohms. We often just use, you know what we like to do? I mean, we could just write that like that, because the letters, a letter and a number together always means multiply, but sometimes we also use brackets for multiplying, so we could do that. All right? So according to this, what we have to do is divide both sides by 2,500. And of course, 2,500, that's just 1, right? And just cancels out, so to speak. And then all we need is to do 80 divided by 2,500, which is going to be 0.032. Not much current is going to go through this heater, equals the I. And that would be amps. I'll put my A in there. 0.032 amps. So it's not a very effective heater, because if only 0.032 amps is going through this heater, there's not a whole lot of electrons going through that, which means that it's probably not going to get very hot. A good heater needs a high current and very high voltage. So maybe what you have to do to make this heater more effective is make the voltage much higher, right? Okay, so that's how you can deal with Ohm's law, the relationship between voltage and current.